Hi, today's topic is inductance. So here I am showing you two coils. One coil which is connected to battery is called primary coil, and you can see there is one adjacent coil kept just in closeness of vicinity of the first coil, which has no any source. It is connected to a galvanometer. This is called secondary coil. So you will find that when I current is flowing through the primary coil, IP current, then a flux will be induced in whole of its vicinity, and that field lines will be also passing through the secondary coil. Due to change of this flux line through secondary coil, and electricity will be produced in the secondary coil, and EMF will be induced in the secondary coil. So the flux related through the secondary coil, phi S, it is produced due to current in the primary coil, so it should be proportional to current of the primary coil. Now here the constant of proportionality given is equal to mu on secondary due to primary. This is your constant of proportionality for the equation, and this constant of proportionality is called inductance. When two coils are used, this is called mutual inductance. This constant is your also it is called coefficient of mutual induction. So when two coils you have used, then you have the constant which is called mutual inductance and has unit Henry. SI unit. Now when you use a single coil in place of two, here also when there is change in current, you will have a change in magnetic field also, and there will be a change in magnetic flux, and due to changing magnetic flux, an EMF is induced in the same coil which will oppose a change in flux. So if flux is increasing, like when your homes you have a tungsten bulb, you can observe this. When electricity comes, firstly there is a very low glow of the bulb, because as the current tries to increase, there is generated an eddy current and induced EMF which opposes the increase of magnetic field lines. So at the initial time when just electricity comes, you have low glow for a moment, and then glow increases. Now when the electricity goes, at that time you will find that it glows very bright just for a moment, and then electricity cuts. What happens then? There is a decrease in magnetic field and magnetic flux while cut off the electricity, because current decreases. Accordingly the magnetic field decreases and the magnetic flux. Now here an EMF is induced in the coil which will try to oppose the change of reduction of magnetic flux, and it will strengthen the magnetic flux. So you will see a very bright glow just for a moment before the cut of electricity. So in the same wire also you can find induction of electromagnetic induction in the coil in opposite direction. Suppose the flux, change of flux is phi, you have flux phi and current flowing in the same wire is I. Then this flux will be proportional to current. For a single coil you have the constant of proportionality called L. This is your self-inductance. You can also call it as coefficient of self-induction. So there are two kinds of inductance. One is your mutual inductance and another is your self-inductance. So let us find one by one. Firstly, I am doing mutual inductance. Here you can see the flux has linked to your secondary coil, but not all the flux. A few field lines, only 1, 2 or 3 field lines are linked with secondary coil. So for finding induction, mutual induction or inductance, we will keep the secondary coil and primary coil with each other by keeping the primary coil inside and secondary coil just wrapping it from the outside. So let the length of the two coils is L only and the radius of inner coil, which is primary coil. Inner coil I have taken as primary and its radius of the coil is R1. Let the number of turns is equal to capital N1 and the number of turns per unit length is N1. It can be written as number of turns per unit length. And the current flowing through the coil is I. Now you have a secondary coil also. Let its radius be R2 and number of turns be N2. Now number of turns per unit length N2 is equal to capital N2 upon L. So using the formula of mutual inductance, we know that flux through any one coil then phi will be proportional to current flowing through the primary coil, current I. Now the same flux will be linked through all the turns because the same field line is there, one field line, two field line. So number of field lines passing through the coils is same. So total flux will be, now total flux through all the turns is equal to N. This is your secondary coil, so you should write N2. Okay, I have taken N2 and let me write it phi 2. This is total flux and this is called, this quantity N2 phi 2 is called flux linkage. So this is your flux linkage, and this will be proportional to the current in primary, current I1. I1 current is flowing through primary cell. Therefore, N2 phi 2 is equal to mutual induction in secondary due to primary. This is your constant of proportionality. Here M21 is mutual inductance in secondary due to current I1 in primary coil. Now N2 can be written as number of turns per unit length into total length, and phi 2, you know that phi magnetic flux is equal to B dot ds, you know. So flux linked with whole of its surface. Let me show you. This is the surface area, ds area. So you can see that you have two surface area, one outside the inner solenoid and one outside the inside solenoid and outside solenoid. So outside there is no magnetic field. In theory you have zero magnetic field outside the solenoid. So this is actually B outside into ds outside plus B inside this inner solenoid dot ds inner solenoid, and this is equal to this magnetic field inside the inner solenoid is due to current in the inner solenoid, and that is equal to mu naught number of turns of primary N1 into current flowing through the primary, that is your I1. This is your magnetic field. Outside magnetic field is 0 plus this is your B inside dot ds inside. Now ds is cross-sectional area, and this is equal to your pi r1 square. So you obtain phi 2. Now N2 phi 2 is equal to, here you have N2 and here you have phi 2. So when you multiply the two, you get N2 L mu naught N1 I1 pi R1 square. So from equation A, here you have equation A, in which flux through the secondary is proportional to current through the primary. So you can equate it on equating B from A. You will find that and mu, okay, let me rearrange it, the given thing. And then I should write. So it is your mu naught N1 N2 pi R1 square L into I1. This must be equal to mutual inductance in 2 due to 1 into I1. So therefore mu 21 you get, which is equal to mu naught N1 N2 pi R1 square L. So from here you can see that mutual inductance only depends on dimensions of a solenoid. It is depending on the number of turns of the both radius and length. mutual it depends on dimensions and property of the space enclosed. If in place of air you have some another medium, then this mu naught will be changed to mu. So mutual inductance then will become mu N1 N2 pi R1 square L. Here mu is equal to mu naught into mu R, where mu R is your relative permeability. Here so it depends on dimensions, number of turns, radius of the inner solenoid. It is depending on radius of inner solenoid and length. It does not depend on the radius of outer solenoid and area of outer solenoid. Now let us do it reversely. So let us think that current is flowing in outer solenoid, not in inner. Everything is same, but the current in this case is flowing through outer solenoid. I just connected the battery in outer solenoid and the galvanometer in to inner solenoid, and then I am doing the same equations like your flux phi through the primary and number of turns through the primary. This must be equal to N1 phi 1. This is your flux linkage. This must be your equal to mutual inductance through secondary. Okay, this is mutual inductance through primary due to secondary, because now current is flowing in secondary coil and the current in secondary. Now here we will do the same things. N1 is equal to number of turns per unit length into L. From this equation, here you can see N2 is equal to number of turns per unit length. So N1 is this much, phi 1. So what is phi 1? Whole magnetic field is uniform from larger solenoid, and that field due to secondary is equal to mu naught N2, number of turns of secondary and current flowing through the secondary. Now the field is same. The same field is here. The same field is inside the inner solenoid also. And flux through the inner solenoid can be written as B1 dot ds. Magnetic field through inner solenoid B1, and it is same as B2. There is no change. The same field is flowing outside, the same field is flowing inside. So B1 can be written as B2 actually, and this is your equal to mu naught and N2 I2 and ds area of inner solenoid. What is area of inner solenoid? It is your pi R1 square. So we obtain N1 from equation 1, phi 1 from 2, And when you combine and put this value in equation A, on combining 1 and 2 and putting the values of 1 and 2 in A, we get that your N1L into your where is it? Okay, something is missing here. Something erroneous I have written. BDS. So this is your equal to mu naught N2 I2 into area. Now this area is area of inner solenoid, that is pi R1 square. Okay. So flux is your mu naught N2 I2 into pi R1 square, and this must be equal to mutual inductance in 1 due to 2 into current I2. So current is cancelled, and you get that mutual inductance in 1 due to 2 is equal to, let me rearrange it, mu naught N1 N2 pi R1 square into L. You find the same value of mutual inductance in the and so M21 is same as M12. Mutual inductance is same of primary and secondary. This idea will be very helpful if you have the length of these solenoids are not same. Now this is a complicated thing. So if you find the mutual inductance in 1 only, then you can say that mutual inductance of 2 will be same as mutual inductance in 1, because you know uniform magnetic field passing through inner solenoid. If it is B2, the same magnetic field, uniform magnetic field B2 will be flowing in shorter inner solenoid also. So you need to find mutual inductance through inner solenoid, and you can easily say that this is the mutual inductance of outer solenoid 2. Idea of having mutual inductance which is mutually generated is very helpful. Now this mutual inductance has been obtained for solenoid, but this is a general solution. You can use this solution in other cases too. Now on which thing mutual inductance depend? It depends on number of turns, it depends on inner radius, it depends on length. For mu, nature of material inside, it depends on length, on inner radius, length, inner radius, and number of turns of the two solenoids. Now it also depends on orientation. If the two solenoids were placed in such a way, then mutual inductance would be different. So it depends on orientation of the solenoids. And it also depends on their distance. If the distance of the two solenoid is large, then there will be less mutual inductance. So this is your 5 and 6th thing is the distance in between the two coils.